Welcome to the Peacademia course on the basics of semiconductors. This lecture covers the bipolar junction transistor or BJT. Let's start. By the time you finish this lesson, you will learn the NPN and PNP BJTs, the structure of BJTs, current flow mechanism in BJTs, and the BJT I-V diagram. So far, you have seen that a PN junction can be used as a rectifier, LED, photodetector, and solar cell. In this lecture, I'm going to show you another dimension of the PN junction capability. In 1947, John Bardeen, William Shockley, and Walter Bradane, who were working in the Bell Labs, observed two gold-pointed contacts connected to a germanium crystal produces an output signal more powerful than the input signal. They called this device point contact transistor. The name transistor is a contraction of trans and resistance. Here is a picture of the first point contact transistor, which was made in 1947. Later, with the progress in the semiconductor technologies, more sophisticated transistors were built, and in this lecture, we are going to look at the bipolar junction transistor or BJT. BJTs are mainly used for amplification and sometimes in electronics circuits as switches. As we will see later, in power electronics, BJTs are less employed due to the large base power loss. In general, BJTs are categorized as NPN and PNP. The reason for this categorizing is simple, and you'll find it out in a few seconds. A BJT is made by sandwiching a P or N-type semiconductor with the opposing semiconductor type. If a P-type semiconductor is sandwiched by two N-type semiconductors, the BJT transistor is called NPN. And if an N-type semiconductor is sandwiched by two P-type semiconductors, it is called PNP. This is the symbol for NPN BJTs, and this is the symbol for PNP BJTs in electrical circuit schematics. The first impression coming to mind after looking at these symbols is that BJTs have three terminals called collector, emitter, and base. For explaining that how a BJT operates, hereafter I developed the discussion for the NPN transistor, but what I discuss about the NPN BJTs will conceptually apply to PNP transistors. Here I have a simple structure of an NPN BJT. First, let's name three semiconductor components of this device. Let's start from the left. The first semiconductor, which is N-type, is called collector. Collector is moderately doped. The middle P-type semiconductor is called base. Base is lightly doped and physically very thin. The right side N semiconductor is called emitter, and it is highly doped. Once the connection between these three semiconductors is made, two depletion regions form. One between the base and collector and another between the base and emitter. This creates a barrier slowing down the diffusion and drift currents between the semiconductors. I already talked about drift and diffusion currents in detail in lectures relating to PN junction diodes. Therefore, in this lecture, I do not repeat those details since I'm assuming that you've watched the previous lectures of this course before watching this lecture on BJTs. Based on the topology of the device, we can consider a BJT as two back-to-back diodes installed in series. Therefore, even if I connect a DC voltage between the collector and emitter, no current can flow. So, if this is the case, how does the device amplifies a signal, or how does the device can perform switching actions? The trick lies in the base. Let's connect a DC voltage source between the base and emitter. I call this voltage source V sub BE. At first, V sub BE is 0 and therefore nothing happens. If I increase VBE, the barrier potential of the depletion region between the base and emitter gets smaller and smaller. And once VBE is equal to the built-in voltage, the base emitter diode is biased forwardly. And now electrons from the emitter can diffuse into the base. Let's imagine N electrons are diffused into the base. Since the base region is so thin, once the electrons arrive at the base region, there is a high chance the electrons are affected by the electrical field of the depletion region between the collector and base. This electric field sucks in most of the electrons and injects them into the collector, and from there they will leave the device through the ohmic contact. A minority of electrons emitted from the emitter is absorbed by the base and leave the device. I think you now understand the reason for the names collector and emitter. Emitter emits electrons, collector collects those electrons going to the base region. Let me call the current flowing through the emitter IE, the current flow through the base IB, and the current flowing through the collector IC. I can write down the relationship between all these currents. IE equals IC plus IB. In BJTs, we normally define two current gains. One is shown by beta and another by alpha. Beta equals IC divided by IB. Alpha equals IC divided by IE. Since IC is smaller than IE, alpha has a quantity smaller than 1. Depending on the doping concentrations of the base, emitter, and collector, the BJT current gain beta ranges from 2 to 30,000. One important thing to take here is that a BJT is a current-controlled device. The reason is that the conductivity from emitter to collector depends on the base current. If the base current is 0, no current can flow from collector to emitter. By working more on these three equations, you can come up with these two equations showing the relationship between the current gains alpha and beta. I already showed you the symbol of the NPN BJT in this lecture. This is the base, this one is collector, and this is the emitter. An identical circuit schematic to the way I bias this NPN transistor is given here. On this circuit schematic, you can see the current directions of IB, IC, and IE. Of course, what I explained about the BJT operation was oversimplified, but enough for us to understand the basics. To gain a better insight into the BJT behavior in terms of the collector and base currents and the collector emitter voltage, it is a good idea to take a look at the BJT I-V diagram. As I earlier mentioned, a BJT is a current controlled device. So if the base current is 0, the collector current is 0. By increasing the base current, depending on the voltage applied to the collector emitter, some current flows through the collector. The larger the base current, the larger the collector current. There is a region in which the base collector current relationship is not linear. This region is called the saturation region. In case we want to use the BJT as a switch, we need to engage the BJT in this region. There is another area called the active region. In active region, the equation IC equals beta times IB is valid. In case we want to employ the BJT as an amplifier, the BJT must be biased in the active region. In power electronics, BJTs are not normally used as a power switch for a very obvious reason. Let's say we have a buck converter that its power switch is a BJT. Imagine the DC current through the inductor is 50 ampere. Normally, power BJTs are required to withstand larger voltages over collector and emitter. Since the doping concentration is disproportional to the collector-emitter breakdown voltage, the doping concentration needs to get reduced. This, in turn, affects the BJT current gain. Although the breakdown voltage gets larger when reducing the doping concentration, the BJT current gain gets smaller. Moreover, as a switch, the BJT must operate in the saturation region in the on state, and the current gain in the saturation region is much smaller than the nominal current gain in the active region. Now that all these are set, if I imagine the current gain for this particular BJT is 10 in the saturation region, the base current will be 5 ampere when the BJT is in the on state. This is a really large current. Think about the gate driver that is going to feed the base of this BJT. The gate driver itself would be a power circuit for itself. This is why a BJT is not a proper switching device in power electronics. In this lecture, I discussed the NPN and PNP BJTs and their structures, current flow mechanism in BJTs, and the IV diagram of BJTs. In the next lecture, I will cover thyristors. Thanks for joining this lecture of Peacademia.